Welcome back, everyone. Hope you enjoyed lunch, even though this year you had to prepare it for yourselves. Hopefully next year we'll be able to take care of it for you. We'll make it up to you. We've got four highlighted talks this afternoon from some of your colleagues. The first is going to be by John Griffith and Lynn Harden from CIRES Education and Outreach. And they're going to be talking about some amazing outreach efforts associated with the Mosaic expedition. Next is going to be CSL scientist Megan Bella talking about the effects of emission, transport, and chemistry on the prediction of air quality impacts from fires. After that, we have CIRES fellow and environmental economist Matt Burgess, who will be talking about 21st century economic growth, climate change, and the impact on society. And finally, rounding out the talks will be CSL scientist Carl Freud, who'll be talking about ATOM's global scale measurements and how they reveal cirrus clouds are seeded by mineral dust aerosol. All of these are pre-recorded, and we encourage you to visit the poster sessions of each speaker to ask more questions directly of them and learn more about these topics. These are going to be part of a broader set of interactive Google Meet room posters, and it's a great opportunity to interact with your colleagues, and I encourage you to look at the posters, engage with your colleagues, ask questions, and just avail yourself of the tremendous activities that are going on at CIRES. Thank you, and enjoy the presentations.
In a world far away from forests and cities, a ship is intentionally frozen into sea ice with over 100 people on board. For the next 12 months, they drift almost continuously across the frozen Arctic at the mercy of the ocean currents, braving long periods of sub-zero temperatures, constant darkness, and total isolation. While attempting to collect data about the Arctic environment and climate system, they must be ready for anything: storms, polar bears, a world that is turned upside down in their absence. It's like a Hollywood thriller, Day After Tomorrow meets The Martian, except it's real and science is accurately depicted. It's Mosaic, the multidisciplinary drifting observatory for the study of Arctic climate.
Mosaic is one of the most extensive Arctic research expeditions ever conducted, and aptly named at that, involving over 500 people from more than 19 nations, including nearly 30 from CIRES and affiliated organizations. It is collaboration at its finest, and the expedition outreach efforts are no exception. Hello, I'm John, and I'm joined by Lynn, and we are members of the education and outreach team at CIRES. Central to our job is to figure out how to disseminate the work of CIRES scientists to the public in the most compelling way possible. At the very least, this requires us to collaborate with scientists, but we've found that it's often in our best interest to expand our collaborative efforts to include folks with a wide variety of expertise and skills, such as teachers, science communicators, media content creators, and more. This broadens the types of materials and educational resources we can create and the ways we can engage folks with them, which ultimately broadens our reach. Don't believe us? Check these out.
Now anyone can learn all about Mosaic and the Arctic with Frozen in the Ice, Exploring the Arctic, a massive open online course featuring more than 30 Mosaic scientists and Arctic experts. The MOOC was made possible through a collaborative effort involving videographers and video producers, communications teams, graphic artists, and others from institutions around the world. Did you know that sea ice has a life cycle? Or have you ever wondered what a climate model wears on the catwalk? These lecture videos and more are free to watch in Coursera and YouTube, and for a small fee, learners can complete the course and earn graduate credit from the University of Colorado Boulder.
Virtual reality Google expeditions were designed collaboratively with educators, videographers, and scientists joining forces to tell the story of Mosaic, connecting the public in K-12 classrooms everywhere to the expedition. This immersive tool allows anyone to hop aboard the Fram, the first ship to be intentionally frozen in ice and drift with Arctic Ocean currents, or join Mosaic scientists as they deploy their instruments on sea ice. These Google expeditions can be viewed through virtual reality headsets or online using the links below. Videographers, scientists, and the CIRES communication team worked tirelessly to develop 2 planetarium shows. The first being the award-winning trailer, Drifting North, which connected thousands of viewers to Mosaic prior to the launch in September of 2019. And we are excited to announce the release of the second show, Into the Polar Night, which captures the first 3 months of the year-long expedition, tracking scientists as they set up their research sites and prepare for the long, dark winter ahead. Stay tuned for a third show, bringing us back into the light next year.
What we've shared here is just a small sample of the wide array of Mosaic education and outreach resources available to teachers, students, and the general public, and made possible by teamwork and collaboration. You can check out our full catalog at mosaic.colorado.edu. Want to learn more about our Mosaic resources and the importance of collaboration in education and outreach? Come visit the CIRES education team today between 1:30 and 1:55 p.m. See you there.
Hello, I'm Megan Bila, a research scientist with CIRES and the NOAA Aerosol Chemical Sciences Laboratory. And I'll be giving you an overview of our research on the effects of emissions, transport, and chemistry on our ability to predict the air quality impacts of fires. This is a very timely topic. We know that over the last several decades, large fires have been increasing both in frequency and severity in the US. We expect those trends to continue with climate change. Those of us who are in Boulder currently have been experiencing the air quality impacts of the Pine Gulch fire, which is currently only 7% contained just north of Grand Junction. The figure on the right shows a prediction of the near surface smoke from the HER-Smoke model. That's a smoke forecasting model that's run here in Boulder at NOAA Esro. It predicts the amount of smoke on a 3-kilometer resolution over the US with hourly updated meteorological fields. And you can see the smoke being emitted from the fire in Western Colorado, transported east across the Rockies and then down along the Front Range. And last night we had a very colorful smoky sunset. So air quality and smoke forecasting models rely on estimates of fire emissions of gases and aerosols that are based on satellite information on fire location and intensity. And depending on the satellite data sources and the algorithms that are used, the estimates of emissions vary widely. This figure shows for October 2017 fires that were burning in Northern California near Santa Rosa. On the horizontal axis, emissions of carbon monoxide. The vertical gray lines show estimates of emissions from different satellite-based inventories. And for this particular day, they range by a factor of 83. And this has real impacts on our ability to predict air quality. On the vertical axis is shown the mean boundary layer concentration of PM2.5. That's particulate matter smaller than 2.5 microns that has the largest health impacts. And you can see the gray lines show for model simulations run with the different emission estimates, what the predicted amount of particulate matter is, and that ranges from minimal, this lower estimate, to hazardous levels. So these uncertainties in air quality forecasting were one of the main motivators for a field campaign that took place last summer by jointly organized by NOAA and NASA called FireXAQ. And FireXAQ leveraged lots of different tools, aircraft, the DC-8 and ER-2 from NASA, 2 Twin Otters from NOAA, some mobile laboratories from public and private sector, and also ongoing data collection by satellites to really look at a range of physical and chemical processes of fires of different types. The campaign intentionally moved partway through from Boise to Salina to focus first on fires in the northwestern US and then agricultural fires in the southeast US. The campaign was extremely successful in sampling a range of different types of fuel and sizes of fire. These are just some examples of fires that were sampled by the aircraft. On the top, there are 2 photos taken from the DC-8 aircraft, the Williams Flat Fire in eastern Washington. This fire was so intense that it triggered a thunderstorm, a pyrocumulonimbus, shown here on the left. And on a personal note, my aunt and uncle were actually evacuated from a summer camp just across the river from this fire. And it had an enormous impact on air quality in the entire region. The lower left was a fire, the Castle Fire burning near the north rim of the Grand Canyon. This satellite photo shows the smoke settling into the canyon at nighttime. Now, as a modeler, usually during field campaigns, I'm on the ground looking at models and using forecasts to try to help the aircraft most effectively sample the fires. But I was lucky enough to be able to go on a flight of this particular fire, and the pilots of the aircraft, who are usually former military pilots, they always like to push the boundaries, and they were able to dip actually over the Grand Canyon, which is a pretty special experience. Now we're just starting to really dig into what the data collected from this campaign are telling us about the chemistry and the physics of the different types of fires. But one example of what we're already seeing is that emissions of volatile organic compounds, which are a key part of ozone formation, the total VOCs measured by a PTR instrument are shown on the vertical axis here, and compared with the ratio of CO, which is a measure of the amount of fuel that's being burned. And you can see that the ratios of VOCs vary widely, almost order of magnitude among different fires sampled during FireXAQ. And this, we believe, is related with the types of fuels and the burn conditions, but we're just starting to untangle these different processes. The FireXAQ dataset is proving extremely useful for evaluating different models that we use to predict smoke and air quality. This is just an example of a flight by the DC-8 over the Central Valley, California, and then Los Angeles, comparing different time series from the aircraft and a regional chemical model. The FireXAQ dataset is the cornerstone of a project at NOAA to develop the next generation air quality forecasting system, because fire emissions have been identified as a key challenge to our ability to predict air quality in the United States. And also to that end, locally here at NOAA Esrael, we have recently started running a new air quality forecasting system for North and part of South America called RAPChem to include the impact of the reduced traffic emissions we've been seeing during the pandemic. We know that there's been a decrease in air pollution in certain regions because of reduced traffic, but in research mode, we'll really start to use the models to understand how these reduced traffic emissions interact with emissions from fires and other sources to affect our air quality on the ground. Thanks for your attention, and feel free to email me with any comments or questions.
Hi, everyone. It's great to be here. Thanks so much for having me. My name is Matt Burgess. My information is on the slide. We only have 5 minutes, so I'll just get right into it. I want to talk about economic growth in the 21st century and some reasons why we should be thinking more about it, especially in the environmental context. And I want to present it as 5 stylized facts with important implications. And these ideas are based largely on these 3 papers in my group, which I'm happy to share with anybody on request. Okay, so the first stylized fact is that economic growth is going to slow down this century. Obviously, nobody's perfectly clairvoyant, but economists overwhelmingly agree that this is going to be the case at the global scale and in most regions, with some disagreement on how much. And to some extent, that disagreement is captured in this range of shared socioeconomic pathway growth trajectories, which are scenarios used commonly in climate change research. And the point is just that they're all going down, even though they go down by different amounts. Okay, number 2, economic forecasts, which are all basically going down in the 21st century, historically have tended to be biased high. So we've tended to have less growth than these models predict we're going to have. And so this is showing this again with in the context of these SSP scenarios in the dotted colored lines, compared to data in the black with projections to 2024 that were made last October added on in each of these regions. And then the gray is showing the revised projections, all from the IMF, that were made in April 2020, which include a pretty fantasy land V-shaped recovery that's unlikely to happen. But even before COVID, these growth projections were still higher than the data, and for reasons that go beyond the Great Recession too. Okay, so growth is slowing down, and it may be slowing down faster than we think if the trend of us overestimating growth continues. Number 3, some of the high emission scenarios used in climate change research make economic assumptions that aren't internally consistent. So one example here, shown in these two figures, is on the left, the SSP 5 8.5, which is the new version of RCP 8.5 in the SSP scenarios, projects that we're going to have per capita GDP in all world regions higher than $120,000 in today's US dollars by 2100. So everybody's going to be, as rich as an entry-level, high-tech worker with a master's degree. And at the same time, these huge swaths of the tropics shown in red in the figure on the right are going to be uninhabitably hot based on these emissions, according to other studies. These two things don't really make sense together. That doesn't mean that the alarmists necessarily have it wrong. It might mean that, climate change is a bigger threat to our economy at lower temperatures than we thought, but it does mean we need to be a little bit careful about using these high emission scenarios. Number 4, I don't think that many people know this, but it's concerning, at least to me. Democracy and growth have largely arisen together historically. So before the Industrial Revolution, there wasn't much per capita GDP growth at the global scale, and there wasn't much democracy at the global scale. And those two things really took off together in the 19th and 20th centuries. And growth is projected to go down. So the blue line is showing historical fraction of the population living in a democracy. The black line is showing historical growth. And then the dotted black line is showing projected growth under the middle of the road SSP scenario, which, as I previously argued, is probably too high. So growth is likely to go down a lot. And then the big question is, what happens to democracy? And then lastly, we have a looming debt problem. So what happens when an advanced democracy has stagnant growth for decades? We've seen that movie in Japan. The answer in Japan is public debt as a percentage of GDP goes through the roof. That's the dark red line. The Congressional Budget Office is already making a similar projection for the US. Shown in the pink line is data, and then the dotted pink line is their projection. And that projection is based on economic growth forecasts that I argued previously are probably too high. So that debt bomb that's coming for us is probably bigger than it looks like here. And so just some quick thoughts for me that I take from this that I love to discuss more with all of you at the Q&A is, first, I think we need to raise taxes. We've got this debt bomb coming for us. We need to make tons of investments in things like infrastructure, clean energy. There's no way around raising taxes if those two things are true. Second, I think we need to improve social cohesion. I think it's going to be more important for maintaining democracy amid slow growth. And I don't think either extreme in the political spectrum is particularly good at this right now. And lastly, if growth is going to slow down, we need to have a broader discussion of climate adjacent risks. So fiscal challenges, conflict, migration, demagoguery, et cetera. I'm out of time, but happy to talk about this more in the Q&A. Thank you so much for having me.
Hello, I'm Carl Freud. I'm an atmospheric scientist at the NOAA Chemical Sciences Laboratory. My interest is in atmospheric aerosol particles, and in particular, how aerosol can affect cloud formation. And this is an example I'm showing you here is mineral dust aerosol as a cloud engulfing the city of Phoenix a couple of summers ago. And this obviously creates some air quality and visibility problems. I'm actually interested in dust more as it affects Earth's climate. We zoom out for a global perspective. We know that mineral dust aerosol are emitted from the Earth's deserts. And here's the biggest emitter, the Sahara, putting a plume out over the Atlantic that you can see by satellite. And these plumes travel across the Atlantic, and as we know, they hit the Caribbean and occasionally, like last month, the US, where they can create air quality problems. I'm more interested in what happens to this dust aerosol after it dissipates into the background atmosphere. And ultimately, it can get wafted to higher altitudes, and that's where it can affect cloud formation. The reason is that mineral dust particles are very efficient at acting as natural seeds for cirrus clouds. These are the high altitude wispy clouds you often see out your window. And they are important, like all clouds are, because they regulate the atmospheric radiation balance, and that means Earth's climate. And so that's a link between dust aerosol and climate and future climate. And we don't have a good ability to predict cirrus formation in the atmosphere right now, nor to predict changes in cirrus formation in the future. Dust aerosol competes with other aerosol types to form cloud, and the question is whether there's enough dust in the atmosphere to affect cirrus formation, because how these clouds form affects the radiative properties and ultimately their global coverage. So I approached this problem by measuring mineral dust aerosol from aircraft platforms. Recently, I had the privilege of participating in the NASA atmospheric tomography campaigns, the ATOM campaigns, and the goal here was to map the remote global atmosphere far from continental sources. We did that by using a heavy lift aircraft, the NASA DC-8, and outfitting it with dozens of instruments, both aerosol and chemical measurements, and we island hopped down the Pacific and up the Atlantic, measuring the whole way, and also not just flying straight and level, but mapping vertically, going from mid to max altitude continuously. And so that gave us effectively a 2D curtain map of the atmosphere. And so this was really a very rewarding mission scientifically, and it was also a great experience for the people who were able to participate. So I thought I'd put together a couple of ATOM stats for you. We had 4 seasonal deployments. They lasted about a month each. We covered 165 degrees of latitude, 9 countries, during which we were allotted 2 small duffel bags for our personal gear and clothing, which included winter gear. We had 48 flights, about 9 hours each, and we covered over 300,000 kilometers, which is most of the way to the moon. During that time, we successfully executed almost 700 vertical profiles of the atmosphere using 40 different instruments, 28 science teams, and I'll point out here that we had 40 CIRES scientists involved, so CIRES really had a large contribution to this study. In the end, we were able to generate over 500 different parameters of atmospheric state, aerosol, and chemical properties that we measured continuously along these flight tracks. One of those was. And so these mineral dust measurements from myself and my team are novel in that we've never had a background atmospheric snapshot of mineral dust like this. So what I wanted to do was step forward a little bit and ask the question, is there enough dust out there to affect these important cirrus clouds? So I did that using an approach that combines our dust measurements with 2 different types of models. First, for each point along the aircraft track, we calculate the forward trajectory of an air parcel, its future. And air parcels that go upward can cool and potentially form cirrus. Those that go downward warm and will not form cloud. Third, at every time point along that future, we run a very detailed, highly computationally expensive model of cirrus formation that incorporates the dust aerosol. It also incorporates how efficiently dust can form cloud versus other aerosol. So I had all these details wrapped up in one model. So this approach brings to bear a set of new tools to the problem and ultimately tries to answer the question more quantitatively, can dust aerosol affect cirrus? And lastly, I'll just show you a couple of quick results. On the left, there's a heat map of the locations analyzed for cirrus formation. This is just where all those air parcels went. So it shows that we've extended what was already a global sampling campaign into a truly global analysis. On the right side is a summary of the cirrus formation events predicted by this analysis as a function of latitude. The brown bars and lines show cirrus that were seeded by dust aerosol alone, and you can see that's the vast majority of cirrus in this study globally, and particularly outside the tropics, accounting for over 70% of the cirrus in this study. It's heavily weighted towards the northern hemisphere because we know it's dustier there. There are more dust emissions in the north than the southern hemisphere. However, even in the south, dust can play a role sometimes during some seasons. And so for the first time, by combining these new measurements with a variety of models, we've got a more quantitative understanding that unequivocally ties mineral dust emissions to these important atmospheric features, these cirrus clouds. Combining these new measurements with a variety of models, we've got a more quantitative understanding that unequivocally ties mineral dust emissions to these important atmospheric features, these cirrus clouds. And lastly, I'll leave you with the idea that future dust emissions are highly uncertain, and that's for two reasons. We don't understand how humans impact deserts and dust formation, and we also don't understand how deserts will change in a changing climate. Thanks for your attention, and please join me at the poster discussion at 3 o'clock today.